Hi, and welcome to a video on Newton's method. There are certainly some animation videos out there that you can look at as well if you want to see this sort of in live form. And Wolfram Alpha has a demonstration as well. But if I show you this sort of statically, let's see if we can get a good view of what Newton's method is doing. So I'm going to try to draw something fairly curved, but okay. So let's say we have some f of x that looks like so, and if we were trying to approximate a zero, approximate what that value is, where does that graph cross the x-axis, right? Well, one technique is Newton's method, and what that says is just make a guess, right, and be decently close. The reason I'm this far away a little bit is because I want to do this 2 or 3 times to show you these iterations and what it looks like. But he says get a guess, right? So some x1, if you will, that's decently close to your zero of your function. Okay, so if I use this and I calculate or write the equation of the tangent line at that point, there's my tangent line at that point, the x-intercept of that line is actually a better estimate than my initial x1 was. And so now I'm actually going to go through Newton's method again, or another iteration of it. So this is maybe like an x2 now, right? This is my new guess. And so I would write the tangent line. Oops, I didn't even go through it. At that point, right, at that x value. And you'll see this guess is even closer, right? So the x-intercepts of our tangent lines at those guesses turn out to be even closer than our initial guess was. And so that might be, for example, x3, and I can do this again in successive iterations until I get as close as I want to, or until that tolerance is built in. And again, if you work with the equation of a line, I'll just put it in slope-intercept form, y equals mx plus b, you can do some rewriting of your equation to figure out, first of all, the slope is the slope of our tangent line, so it might be written something like f prime of x, and our y is our f of x, right? So I might see something like this. And b being the y-intercept of that line. So again, I can solve this in different ways, but I come out with this table right here where I'm going to use this table and kind of fill this in. So I'm going to have to make an initial guess, x sub n, evaluate my function, right? So what's the y value there? What's the first derivative, which is going to give me the slope of the tangent line? Then that ratio, because again, I'm going to have to solve basically for that x value. And then when you subtract it there, you're getting your new guess, right? Your next x sub n. So here's the first example that we'll go through. Approximate the zeros of this function. Use Newton's method and continue the process until 2 successive approximations differ by less than 1/1000th. So that's our tolerance, and here's our function that is given. So one thing, because we do have modern technology on our side, is I do think we should come up with an educated first guess. There's different ways of doing this. You can use different things you've learned throughout your pre-calculus experiences, like Descartes' rule of signs. You can use different curvature ideas and behavior ideas, zeros, all of that to help you graph this function. Or you can also use your technology to help you graph this. Again, I don't think we should just be graphing blindly anymore because we have technology on our side. So I'm going to look at y equals, and I'm going to type in the function 3 minus 2x cubed. And I'm just going to zoom 6 because I don't know what window I was in last. And I'm just looking for approximately where does the 0 look like it is. So this function appears like it crosses the x-axis at about 1. So I'm going to say let's let our first guess be a 1. And then I have to do a bunch of calculations. If you would like to do these calculations on your own, that's fine. I'll do them first on my own for this first row, and then from here I'm going to let my table sort of help me out. So f of 1 would be 3 minus 2, so it's going to be 1. But I do need an f prime. So f prime of x is derivative of 3 would be 0, so negative 6x squared. And so if I put x equals 1 in there, I get negative 6. If I divide these, I get 1 divided by negative 6, but I'm going to need the decimal because, again, I want to make sure that I'm less than 1/1000th in the end, so I want to see these as decimals. So basically, if I want to be accurate to that third decimal is what they're trying to suggest here, then I want to go out to 4 decimals in my work. So if I divide that, I should get negative 0.1667. So this tells you how far away basically you were, right? So my new x value will be my x, right, that I started with, which was 1, minus this amount. So I'm going to say approximately again because this was a rounded value. So guess number 2 here, or iteration 2, should be 1.1667. And this gets to be the point where I say I'm not going to do this anymore, in my head or on my paper. I'm going to let my table help me out. So in my y1, I'm going to put the original function, and in y2, I'm going to put the derivative, and since this was an easy enough derivative for me to calculate, I just calculate it. Otherwise, you can use your NDeriv, your numerical derivative feature. I'm going to make sure in my table set or second window that I'm able to type in values into my table. So I go to independent, click ask. Most of you are probably already have that set. So now it's waiting for me to type this in. So my x value was 1.1667. So my original function, and again, I want to hover over these values because your columns are pretty small, so they're not going to have room to write the whole number. So I can see that it truncates it off, in other words. It's not going to have room to write that whole thing. So negative point, I'm going to round to 4 decimals again, 1762, negative 0.1762. Then for my first derivative, again, I want to hover over that because I can only see 3 decimals and I know it doesn't end there. So now I can see 4 decimals, negative 8.1671. Now I'll divide them. I can divide them on my home screen, or I'll show you a way I can actually have my table. I can have a y3 in here if I wanted to of what y1 divided by y2 would be. So if I go back to my y equals, I can put that in here, and again, you want the original function over the derivative, so I want y1 divided by y2. So if I go vars, which is kitty corner from your arrows, go over to yvars, function, hit enter on y1, divided by, and we'll do that again. Vars, go over to yvars or y variables, hit enter on function, and now arrow down to y2 and hit enter, and now I have that ratio. So now when I go back to my table, I have a third column in there, after my x of course, of this ratio. So that would be 0.0216 if I round to 4 decimals. And so I'm taking my initial guess in this step, which was 1.1667, and I'm subtracting this off. And what you should be seeing is that you are getting closer every time. First I was off by, negative 0.1667, or a little bit more than a tenth. Now I'm only off by 2/100ths. So I'm going to be getting closer and closer to what I think is this approximation. So This is going to be, and again, you can do this from your home screen. This is where I usually will choose to do these subtractions. So I'm just going to say 1 point, and I can probably do this one faster in my head, but that's okay. 0.0216. Copy that right. 1.1667 minus 0.0216. Yep. 1.1451. So that is my iteration or guess 3. But when I go to my table now, a lot is ready for me. So I go to my table, I calculate 1.1451, and I can look at these values. So negative 0.0030, if I put that into my function. The derivative value, or the red, the y2 would be negative 7.8675, negative 7.8675, and then the ratio, it appears, this e negative 4, it appears like it's 0, but we're going to write it down. So it'd be 0.0004 if we round to that fourth. So now this is telling me that my actual, or getting closer to my actual x-intercept, or 0, would be this guess, 1.1451 that we started with. Now you're only 1, 2, 3, okay, 0.0004 away. I can subtract this 1.1447, because if you subtract 4 from 51, you get 47. But what I want you to notice is, again, this is telling you basically how far off you were from your previous guess. So in other words, if you rounded these to 3 decimals, you would get 1.145 both times. So this is my x-intercept, if you will, rounded to 3 decimals. And if you wanted to check that, you have this on the graph for y equals. I'm going to turn off temporarily the other 2 because I don't necessarily want to get distracted by that. But if I go back to calculate a 0 on my graph here, it's only showing the original function, and I can go to left bound, so just to the left side of it, hit enter, go to the right side of it, hit enter, and then get decently close for a guess, hit enter, and I can see that my 0 is, in fact, if I round to 3 decimals, 1.145. So Newton's method works. So let's do this again and see how we can use Newton's method to find intersection points. So we're going to apply Newton's method to approximate the x value of the points of intersection, again with the same level of accuracy. So one thing that it's important to note is you do still need to get a first guess, right? So my first guess is going to be approximately that they're intersecting at x equals 3. I did label the line because here's your functions. I did label the line f of x. And that curve there that we'll study a decent amount throughout calculus, g of x, because that's that 1 over x squared plus 1. So it appears my first guess is going to be a 3. But in our y equals, we want to be working with only one function, right? What is your function of x? What is your derivatives in terms of x? So I want to subtract these curves so that I'm looking for a 0. So if we take, for example, f of x minus g of x, and let me just write this up here maybe. So if I'm solving where does f of x equal g of x, another way to do that would be to subtract, for example, g of x from both sides, and now you're looking for a 0. Again, you could have subtracted f of x from both sides, so you could say 0 equals g of x minus f of x. It really doesn't matter. So what I'm going to put into y1 is this function over here. The line 3 minus x, right, which was my f, minus my g. And so I will come over here and change my y equals. And I'm also going to remind you how if you don't need the algebraic derivative, you can actually let your calculator do that for you, which if you went through some of the previous videos, you might already know how to do that. So there's my y equals 3 minus x minus 1 over that quantity. Okay, so now if I don't want to necessarily calculate an algebraic derivative, I can let my calculator calculate a numeric derivative. So if you go math, you have a numerical derivative, math choice 8, and you're going to say, I want to take the derivative with respect to x of y1. So that's that vars. Go over to y bars, hit enter on function, hit enter on y1, and I want to do this right now for all x in its domain. And then I can still say that I want to take y1, so vars, go over to y vars function y1 divided by y2. For that ratio. So now when I go to my table, I'm going to delete out the other x values because those aren't important to this problem. I want to start with x equals 3. So, and if I again hover over just to make sure it's not just not showing me stuff or that it's, rounding, and there I can see that it is in fact rounding, but I would round to the same. I can see what these are equaling. So I'll copy those onto my chart. And then now that I have those on my chart and I can see that ratio is 0.1064, so I'm going to go back to my home screen and say what is 3 minus, just to be safe here, 0.1064. So that should be 2.8936. So this guess will be 2.8936. So my second iteration or go around will be 2.8936. I'll go back to my calculator. I'll go back to my table and I'll put in an x value of 2.8936. And I will write down all those values on my chart. Now just be careful. I'm going to write down negative 0.0003. And then my derivative value is the red, so that will be negative 0.9341. And so this ratio turns out to be real small as well. It's 0.0003. And if you're not sure how I'm getting that, that's because of the e negative 4, so it's scientific notation times 10 to the negative 4. So you take this decimal point and you move it 4 places to the left. So then this becomes 2.8936 minus 0.0003. So this is approximately 2.8933. Now technically this one rounds to a 4 while this one is going to round to a 3. So I would do one more iteration just to be safe here with the 2.8933 and to see where we end up with that one. So you can pause and try to do this on your own if you'd like. Otherwise I'm going to fill this in for us. And so once I fill that in for the 2.8933, I did actually have to go out to one additional decimal, otherwise this is going to look like 0. So this will become still the 2.8933. So if we were rounding to 3 decimals, I would say this intersection is at approximately 2.893. So let's just look real quick here at this last example of why Newton's method fails. Now, it doesn't mean that we can't use Newton's method. It just really means that the values that you chose are not going to work. So let's take a look at why. So if I have this function right here, which is a third degree polynomial, I've kind of sketched it off to the right there for you. And let's see why if you use 1.5, which is that guess up here, why does Newton's method not work? So my first guess is 1.5 or 3/2. And so again, now if I go back to my calculator, the nice thing about putting in the derivative as a numerical calculation and this ratio as a general y1 over y2 is that the only thing I have to change out is y1 each time. So this is 4x cubed minus 12x squared plus 12x minus 3. And then I can go to my table and everything should be ready to go for me. Again, I'm going to delete, delete, delete because those are values that I don't need. I need to talk about 1.5. Okay, so let's see here. If I evaluate my function at 1.5, I get 1.5, then 3, and then 1/2. So when we divide this, we end up getting 1/2. So really, my second guess should be a 1. So my second guess, I will use a 1. And I can usually calculate pretty quickly here without using my calculator with a 1. So I'm going to calculate this derivative real fast. Okay. So my function value at 1 would be 4 minus 12 plus 12 minus 3. So 4 minus 3 is 1. My first derivative at 1 is going to be 12 minus 24 plus 12. So 24 minus 24 is 0. And this ratio becomes 1 over 0. What you might have found if you did it using your calculator is something that looks like this. So it calculated the original function correctly at 1, but then it's basically trying to tell me that that's 0. And so remember, this ratio is kind of telling you how far you're shifting that over, because that's what you subtract from your x value to get your next guess. Something as big as 250,000, there's no way that we are 250,000 away from our guess. So if you were using your calculators, that's that idea that 1 over something really, really small is really, really big, right? So it's telling me that this cannot be calculated. So what happened was, oftentimes if our actual is too far away from our guess, or if we have a turning point, which I do, in between there, it might not give me the results that I want. Now, if my actual was in between 0 and 1 like that, and I'm guessing something like 1.5, I'm pretty far away. If I guessed something like 1/2 to start with, Newton's method would have worked. So it doesn't necessarily mean that Newton's method won't work for any value. Newton's method just failed for the value that you chose. So you just have to be careful that you're picking something decently close. I hope you found this helpful on Newton's method.